Welcome to our 11 o'clock press conference. This is the last one of the meeting. We're calling this one Changing the Energy Landscape, More Efficient Wind Farms and Cleaner Biofuels. We have three speakers who will speak in this order. Martin Graus, research scientist at NOAA Earth System Research Laboratory and the Cooperative Institute for Research in Environmental Sciences. This is at the University of Colorado in Boulder. Julie Lundquist, she's assistant professor, Department of Atmospheric and Ocean Sciences at the University of Colorado Boulder. And Yelena Pichugina, who is research scientist with NOAA Earth System Research Laboratory and Series as well at the University of Colorado Boulder.
Well, thank you for your interest in our research topic, trace gas exchange between biofuel crops and the atmosphere. I'm Martin Graus. What is this research about? If you wanted to boil it down into one question, it would be, do we have to expect poor air quality from growing biofuel crops? And this might be kind of odd question, biofuel crops, greener energy, and air quality problem. But as you may know, plants emit substantial amounts of volatile organic compounds, VOCs as we call them. And VOCs, not only from cars and industry, but also from vegetation, can act as precursors for ozone and aerosol. So do we really have to expect poor air quality from growing biofuel crops? The short answer is probably not, but let me go into more detail. The US is the world's largest fuel ethanol producer and produces this ethanol dominantly from corn. To give you an example for the size of this operation, last year in the US, an area of the size of Germany was planted with corn, and a third of the US corn crop was turned into fuel ethanol to cover about a tenth of the American gasoline consumption. And there's more increase to come, not only in the volume of biofuels added to the gasoline, but legislation also specifies that more than half of this biofuel ethanol or bioethanol must not come from corn but from cellulosic feedstock. So at the moment we have corn as the big player, and in the future we might have plants like switchgrass as an even bigger player in this energy source. So it seems only prudent to look into the life cycle of biofuels. And there's lots of interesting and important aspects to the life cycle of a biofuel. And the aspect that our research looks into is the VOC emissions from growing the feedstock for the production of biofuels. We did that in a very thorough approach with lab experiments on potted plants in growth chambers. We also took our sensitive instruments out into the field and put corn and switchgrass into enclosures where we put leaves in. And we also did experiments on whole ecosystem fluxes using a technique called eddy covariant technique. To jump into the experiments, as you may know, corn is a very fast-growing crop. Within 6 weeks, you go from knee-high to 6 to 7 foot tall plants. And during the growth of corn, for example, the amount of corn grown to produce 1 liter of fuel ethanol equals the VOC emissions of about 8 grams. And for switchgrass, it would be about 6 grams. But not all of those VOCs in the mix, not all of those compounds in the mix of VOCs that are emitted have the same properties. We have compounds here on the right that are very reactive and have a higher potential to contribute to for example, ozone production. And we have compounds that are less reactive. If you compare the biofuel crops, corn and switchgrass, to other plant species that are suggested for the biofuel production, particularly if you look into tree species that are suggested, we can see on the right-hand side the emissions from tree species of monoterpenes and isoprene is significantly higher of those of switchgrass and corn. So to come to a conclusion, corn and switchgrass are low VOC emitters, and particularly the amounts of reactive VOCs in the mix of emissions is very small. So an adverse effect on air quality from growing of biofuel crops, switchgrass and corn is unlikely. And if you would like to hear more about the science that we're doing, there's a talk, I give a talk tomorrow in the afternoon, 3:10, over at Moscone South in room 301, or you please contact me by email. And I want to point out that this is a research that is done by many, many people who contribute to the results that we come up with. Thank you very much.
Well, good morning, and thank you for your attention. I'm Julie Lundquist from the University of Colorado at Boulder, and I will like to share some news that we have collected in recent months about our observations of wind turbine wakes. And obviously, wind energy is one of the large contributors to renewably generated electricity in the United States, hence our interest in this topic. So I'm part of two large collaborative teams investigating the behavior of wind turbine wakes. And in our teams, we often take for granted that everyone we talk to understands what a wake is. But in case that's not a reasonable assumption, I've shown this picture here from one of Leonardo da Vinci's sketches where we have nice, smooth flow, in this case water, becoming turbulent and a little bit slower as it encounters an obstacle. And this is exactly what happens when the wind encounters a wind turbine. We have nice, smooth, mostly non-turbulent air entering a rotating disk, and behind that disk, the air is more turbulent and moves slower. Now, this is interesting not just for fluid dynamicists, but it has repercussions for those who would like to use energy from the wind. We've observed that the character of the wake of a wind turbine depends on the nature of the air that comes in to the front end. And so we have designed and carried out two studies which intend to look at how we can improve overall wind farm efficiency and ultimately decrease the cost of electricity by better understanding wind turbine wakes and how they behave. And this is a picture from the National Renewable Energy Laboratory's National Wind Technology Center in Boulder, Colorado, where one of these studies took place. So the first study is TWIX, the Turbine Wake and Inflow Characterization Study. This is a large collaboration between NOAA, and in fact, Yelena Pichugina is part of this collaboration, myself at CU Boulder, the National Renewable Energy Laboratory, Lawrence Livermore National Laboratory, who's also represented here today, and we were funded by the Department of Energy. We were looking to understand how far downwind from a turbine does this region of turbulent or slower air persist? How does that plume of turbulent air meander, and how does it spread downwind? Does it ever intersect the ground? And if it does, what might the impacts be? And then how does the wake change with atmospheric variability? We're also interested in simulating these wakes so that when we look at long-term visions of how much electricity can we produce from the wind, we'll be able to account for these wakes in simulation world. So for this study, we deployed NOAA's high-resolution Doppler LiDAR. This is a scanning LiDAR that basically emits a beam of light, measures the backscatter from particles in the atmosphere, just as a police officer would measure the backscatter from your car should you be speeding down the freeway. And that quantifies the wind speed as well as the turbulence in the wind. So we used that instrument, along with several other standard instruments, to characterize the inflow to and the wake from one of the multi-megawatt turbines at NREL's National Wind Technology Center. Now, it's important to note that we used a modern industrial-scale turbine in this experiment rather than smaller turbines which have been used in previous studies. That's one main difference between our investigation. The second difference is that the resolution of the NOAA instrument is 30 meters along the range of its beam, and other studies have used coarser resolution. So we have more information about how the wake meanders and spreads. And here's our aesthetically pleasing picture of the NOAA Hurdle LiDAR at the NREL site. And here's our even more aesthetically pleasing picture for people like me of what a wind turbine wake looks like. And I'll get into the details of this picture in subsequent images. So I'd like to help you understand a little bit about what these data mean. So this direction is running from south to north. This direction is running from east to west. And our scanning instrument, the NOAA instrument, was positioned right here. The colors denote how fast the wind is moving, where warmer colors like yellow and brown and red are faster wind, and cooler colors like blue and green are slower wind. The turbine is located here at the black gap in the data, and you can see clearly the plume of slower air meandering downstream from the turbine. So we've prepared a visualization of 2 hours of what the wake does as it meanders and moves back and forth in the atmosphere. So you can see that the atmosphere itself is always changing. Wind is speeding up, wind is slowing down, but the wake itself is also moving back and forth during this time period. So the initial results that we've seen that I'll be presenting tomorrow in the scientific session is that we see the largest wake deficits 2 to 3 rotor diameters downwind of the turbine. So a rotor diameter of a turbine like this is about 80 meters wide. They extend from 40 meters above the surface to 120 meters above the surface. So the largest wakes are about 160 to 240 meters downwind of the turbine. And we see larger deficits at nighttime conditions, regardless of the wind speed, which is interesting and a little bit of a surprise. At night, we also see longer wakes, and we also see narrower wakes. The second study I'd like to highlight is the CWEX study, the Crop and Wind Energy Experiment, where we're also looking at wind turbine wakes, but we're trying to immediately assess their effect on crops growing in the vicinity. And I have to say I got a little bit nostalgic when I was looking at Martin's pictures of corn growing, because I spent a lot of time in cornfields this summer, along with several people in the audience here, and that corn does grow very quickly. This is an ongoing study, so I'll be reporting on results from last summer, but we are continuing this investigation next summer. It's led by Iowa State University. Gene Tackley from Iowa State is in the audience here. And we're trying to understand if wind turbines might reproduce the known benefits of planting rows of trees in crops by slowing down the wind and enhancing the turbulence in ways that are beneficial for crops. So the collaboration this past summer was between Iowa State, CU Boulder, the National Renewable Energy Laboratory, and the National Center for Atmospheric Research, and we're currently designing our experiment for next summer, for CWEX 12. So the approach that we've taken there is, instead of using one scanning LiDAR going back and forth, we've positioned 2 vertically pointing LiDARs to measure the winds before a turbine and then after a turbine, so we can subtract the difference and look directly at the turbine wake impact. We've found that, again, winds are slower in wakes, and at night the winds are slowing down more. The biggest decrease in wind speeds are found well above the hub, or the center point of the turbine. And at night, we also see the largest increase in turbulence in the wake. And those differences do not degrade very much with distance. And they also extend as far down to the surface as our LiDARs can see. And that's 40 meters above the ground, which is still well above the ground. But this is suggestive that when the Iowa State team finishes analyzing the surface station data, we may be able to see an effect of wakes on near surface meteorology and therefore on crops. So I'd like to show you a sample of these difference plots where we've taken turbulence, which here we've called TKE, turbulent kinetic energy, and subtracted the upwind measurement from the downwind measurement. And you can see that we have substantial differences over this 9-hour time period in the region 120 meters or below, which is the region that the turbine rotor disk encounters. And these differences are well beyond what you would expect to observe. So it's interesting that they're so large, perhaps because we were measuring so close to the turbine. Michael Rhodes, a graduate student working in our group, has presented this poster this morning and is also available to help answer questions about this topic. So thank you for your interest.
Good morning. Let's switch gear and talk about offshore winds. Investigating the unknown at turbine rotor heights. Today, I'd like to show you how scientists from NOAA and CIRRUS use advanced instruments to study marine winds at the height of modern multi-megawatt turbines. Nowadays, all the information available of below 30 meters. And this information not truly reflects what is going on at the height of 50, 150 meters. And the lack of the information is a big challenge for wind energy development, because managers want to know where to site wind farms, how their turbines will operate, in which conditions. They want to keep high energy production at low maintenance cost. And if there is some measurements from LiDAR or other instruments and toll towers exist in the land, there is none in offshore areas. And to install toll towers taller than 100 meters above the water, it will take a lot of time, it will be very expensive, and also those data will provide only pointed data. That's why scientists use an instrument, and Julie talked about this a little bit, it's Doppler LiDAR. Doppler LiDAR is a remote sensing scanning system that emits eye-safe infrared light, and this beam of light reflected from particles in the atmosphere and bring information to us about wind speed, wind direction, and turbulence. LiDARs deployed on research vessels can provide information on marine winds. Data obtained twice per second later could be averaged over 110 minutes interval and provide us data in vertical for every 5-10 meters. It's very high resolution and perfectly suits for wind energy needs. And data also could be obtained with precision less than 10 centimeters per second. In order to get this precision in the ocean, we need to deal with wave motions. These animations on the top left corner show real conditions in which LiDAR operates in the sea. So our engineers were able to develop unique motion compensation system that allows us to get data with needed precision. Over the last 15-20 years, we use Doppler LiDARs for plenty of measurements inland and offshore, and mostly objectives of those measurements were a little bit different than wind energy objectives. It was like air quality studies. But during all experiments, we had measurements of wind properties. That's why when we don't have any measurements on wind speed and direction offshore, we decided to reuse existing data sets and reanalyze them from the point of view of wind energy needs. And here are some results. The top left slide is Google map of ship track segments along with measured wind speed. And wind speed here given by color. So even do not go into any details, you can see how different color close to the shore or in open ocean, in one part of the shore, in one part of the ocean, in the different part of the ocean. So this data gave us special differences in wind speed. The bottom two plots show just examples of wind speed and wind direction profiles. You also can see how they have a different shape, and also we have plenty of times when the wind direction or wind speed suddenly change. And this is a very huge challenge for wind turbine operator, those rapid changes that we call ramps. When we put all those profiles together for 24 hours, you can see time, height, cross-sections like on those two plots on the right side. And those show wind speed and wind direction shown by black arrows. Wind speed in color, shown for 24 hours period. What is going on? And from 0 to 500 meters. And again, you can see how different situation in wind during 24 hours period for daytime, nighttime. The two horizontal lines in each plot reflect the height of turbine rotor, 150 meters. And you see that turbine rotor operates in different conditions. And you can see from those examples how different conditions for two consecutive periods, July 30th and July 31st. In my conclusion and summary, I want to one more time to stress that Doppler LiDAR is powerful instrument to study offshore winds at any scales relevant to wind energy. And this information very critical for wind farm siting and operation. And LiDAR can provide information, as I showed, on variability of wind speed in space, time, and with height. The existing data sets are short, relatively short. It's 2-3 months measurements. They cannot provide us annual statistics or a climate of wind, marine winds, but they could be used to validate numerical models. They can support satellite information on wind resources. They can supplement development of wind resource maps. And again, there is no any measurements similar to Doppler LiDAR measurements exist in offshore. Thank you very much.
Thank you, speakers. Okay, we'll go ahead with questions. Before we do, I just want to mention, which I forgot to mention earlier, that Julie Lundquist has some handouts on the back table about her work.
Steve Benko with Physics Today. I have two questions about the wind wakes and crops. Okay, first question is, what can the LiDAR measurements that you have actually tell you? I mean, doesn't it make more sense to do observations at 3 or 4 meters elevation rather than, 30 or 40 or 100 meters elevation where the crops don't even live? And I guess a follow-up to that is, what observations are there at that elevation? And then the second question is, just observationally, looking at the crops, what effects do you see downstream versus upstream?
Sure, I'm really... Can you hear me? Is this... Okay, so I'm really glad that you're asking those questions. Those are very good questions, and with just 5 to 7 minutes, it's hard to explain everything that we went through with the experimental design for this. The LiDARs are only one component of the crop-wake interaction study. In this region of the Great Plains, the wind is blowing at one direction at the surface. It's not necessarily blowing in the same direction aloft. And in fact, at night in the Midwest, there's a lot of rotation with height. So it's important, if you want to understand how a wind turbine wake is affecting the surface, it's important to know where the wake actually is. So if you only had surface-based measurements, and the wind was blowing directly between you and me, we might think that, oh, that's where the wake is. But if aloft at the turbine level, the wind is actually blowing in this direction, the wake from that turbine will have no impact on the crops between you and me. So we use the LiDARs to identify where the wakes are going aloft as the wakes are generated from the turbine. Then we have a very dense network. Well, it will be more dense next summer, but this summer we had, I think, 6 or 8 surface stations that are operating at 3 meters above the surface and 10 meters above the surface, measuring the fine-scale interactions of the crops with the atmosphere. But we don't know how to label those time periods of data from the surface stations unless we know where the wakes are. And so that was the reason to have the LiDARs measuring the upper altitudes. Okay, so I think that that may answer your first question. And then your second question was observationally, what type of impacts can we see? And I have to say, when you're standing in a cornfield, it's really hard to see a difference between one piece of corn and the next. And I don't have very refined corn-gazing eyes, and so Jean might be able to comment about this. But I think that it would be a little premature to comment too much on what we saw visually, because, you know, as Martin can attest, you have to do very refined studies on crops to be able to quantify an impact. But you can notice crops near roads, for example, where it's more turbulent, tend to thrive. They tend to be taller. They tend to, you know, enjoy that extra mixing. So, you know, we can comment in only a very casual way right now, and the more mature results will come later. Thank you for the question.
Hi, Mason Inman with National Geographic News. I was just wondering a little bit more about how the turbulence helps the crops. Does it mix, you know, volatile gases that they're putting out, or get them more CO2, or, you know, what does it do?
And that's a better question for a plant physiologist, and I wish I knew more about plant physiology, but my limited understanding is that the more mixing, you can take away waste gases from plants and then bring the other gases that they need to grow in closer to them.
Do we have any other questions?
Kimberly Ayers from KQED's Climate Desk here in San Francisco. We, of course, have a lot of wind farms going up, especially in the Mojave, down south where I live. And how do you see, if you can, either one of you, Yelena or Julie, how do you see a company using this information? Is it just for placement, or is it when to run them, time of day, any other objectives that they might be mining your information? How do you see them using that?
Okay, there's lots of different ways that they could use our measurements. So the measurements of wakes, you know, very few wind turbines are set up on their own. So most turbines are in the wake of another turbine. So most new wind farms are very large, you know, hundreds of turbines. So the information that we have about how the wake from an upstream turbine will affect the downstream turbines can let the wind farm owner-operators know how much power they'll be producing, because they can correctly account for wake effects. If they know how much power they're producing, they can bid more competitively on the open market, which would eventually reduce the cost of energy. So that's one example. And latest detailed profiles of the wind might be useful as well.
And also it's very important for siting of how close wind turbines should be to each other, because if they too far, the maintenance cost will increase, but if they're too close, there is the turbulence and potential damage the turbines in the second row. So it's very important information for wind developers.
Also, just a follow-up to that. I would imagine one of the concerns that has come up in the Mojave is the wildlife below the turbines. And can you just comment about at least how that information, your information, the low-level informations might play into at least knowing what some of those consequences or effects might be?
Actually, we are looking for collaborators in the ecological fields who know more about which types of birds and bats are sensitive to temperature and turbulence fluctuations. So in designing future experiments, we're looking for collaborators. So those of you in the room, if you know anyone, or those of you on the webcast, please send them in my direction. Thank you for asking that.
This is Douglas Fisher with Daily Climate, and I guess I want to follow up a little bit on that. Is other ecological impacts that might you either want to investigate or hypothesize are as a result of these turbine wakes, and whether it could be whether it could have a landscape scale impact as these turbines spread?
Go ahead.
Okay.
And I will talk about
Okay, so I'll focus on the land issue, and Lane is going to focus on the offshore issue. So in my discussions with people who look at ecological impacts, one of the biggest questions they have at the beginning is what creatures are there to be affected in the first place. So before we incorporate ecological impacts into a design, we have to find a location where we know what creatures are there and what their patterns are before we can speculate how they might be affected. And there are several research networks that are forming now to take atmospheric dynamicists and observationalists and connect them with the ecological impacts people so that we can design experiments that can satisfy issues of what are the atmospheric impacts and what are the ecological impacts. So again, if we need to talk about a specific location to talk about which creatures might be impacted, and I'm not knowledgeable enough yet about that. But this work is definitely of great interest in my community, and we're moving in that direction.
And similar for the offshore wind farms, in order to site wind farms in any place, the developers have to get a license first, and plenty of people will work on it, and ecologists and environmentalists and policy will be involved. So they will look very carefully where they let those wind farms to be sited. And in offshore, mostly we are talking about wind farms sited 6-20 miles of their coast, so the visual impact will be minimal for the people, and the benefits could be huge, especially in the east coast, because this area close to big load centers, and so the transmission cost will be not so high like if the transmit energy from Great Plains, for example.
Where do international waters begin? How far offshore?
Yeah, US a little bit behind Europe, because plenty of offshore wind farm already developed, especially in Denmark, Great Britain, Germany. So, and we have to just catch up with those countries. Did I answer your question? Nope.
What I meant was, where do national waters separate from international waters? I mean, how far offshore? I forget how many miles offshore that is. How many?
Yeah, I think up to 30 miles, and it's okay. We can, it's national waters.
And I had a question about offshore wind, and for how plausible would it be to do large surveys with this LiDAR of the offshore wind? Would you have to just pick a certain area where you thought it seemed promising, and then people might be able to scan that and see, or could you do, the whole West Coast? Or what would be plausible?
Yes, of course, we will use previous knowledge about the potential areas, and we'll start from those potential areas. Like we know right now, the Cape Cod is the best place to develop wind farm. There is plenty of factors should be considered at the depths of the ocean, close to the load centers, and so on. And when we choose first, based on the other measurements or historical knowledge, the area, then we will put Doppler LiDARs on a research vessel and cruise through this along the coast, find the best place to sit farms. And it will be, Doppler LiDAR can provide spatially distributed data up to several kilometers in horizontal. So it's not like put one tower and it will give you data only in one point.
Do we have any other questions? Any questions from the chat? Okay, well that wraps it up. thank you very much for your presentations, and thanks everyone for having been here. This is it for the press conference schedule for this meeting, so we will not be having any further press conferences.